So now we're going to talk about the technologies sort of one by one going forward here for really the better part of the day. Moderating this panel is Mark Hughes of the Kleinman Center at Penn, who got the last flight out of Philadelphia. And I think Armin Cohen has joined us from the Clean Air Task Force, who got the first flight out of Boston this morning. So we're very happy everybody's here. But Mark is a great partner for us. And in his background as a urban design thinker, and also a sustainability manager for the city of Philadelphia for a little while, has a lot of great background on this. And the reason we didn't move panels around, because he has two virtual speakers, is that if anything goes wrong, he can handle it. So, Mark, and that mic is working.
All right, thank you, David. That's just David's very generous way of saying that as an academic, he knows that I can talk for 10 minutes or 10 hours with no change in total content. And so if there's any downtime, I'll try to help fill it. But I don't think there will be. I think we've got a great panel with three speakers. I just want to do some quick table setting. And begin that table setting by thanking PEC. They've been amazing grace under fire with all of this. I can speak for, as you know, the guy who got the last flight out. There's been so much disruption, and they've just handled and responded to everything so well. You really have the stamina of a steward. It really shows on that. So thank you and congrats for all of that stuff. I also just have to say, to Neil and Granger, those were two fantastic kind of keynote framing talks. And I just wanted to emphasize 2 points. One was this masterclass in stylized facts, right? It probably doesn't matter in a room like this much beyond the demonstration effect of teaching us all the importance of doing it. But certainly outside this room, most of the votes you're trying to whip, most of the influence most of the opinion you're trying to influence, most of the minds you're trying to educate, really don't care, can't retain, and don't need to know whether it's 31 or 37. And then second, this point that both Neil and Granger raised about the importance of a political strategy in the pathway beyond the technology mix, which I think is one of the things as we move into these technology channel panels, I hope we talk about in the Q&A. I know we'll talk about it in the presentations. The importance of understanding, you know, when you refer, for example, to the California exception and note the importance of Pennsylvania's participation in that exception, right? People, I think, in this room, and certainly those speakers, understand the importance of that. But there's so many weak political theories floating around after the presidential election about how this is going to be a golden era of subnational government response and leadership and innovation. And I think that's a fundamental misreading of what happened, right? This is not a national administration that believes necessarily in federalism, right? And these are nationalists who believe in strong national policy. And I got one word for you, and it does in fact start with P, for those of you who've seen The Graduate, and it's preemption, right? The preemption of subnational discretion around the kinds of issues that we're talking about is a big possible problem for these conversations. And so, but the larger point about that both of those speakers illustrated so nicely was the importance of the political theory, the understanding of the feasibility in addition to the technology. So I just want to say the basic agenda here for this panel is that we will begin with Jesse. Jesse, I'm so glad that you're able to kind of feed in. And we'll slide directly into the other two shorter presentations that will be partly reaction, partly extension of Jesse's comments. First by Eric and then by Steve, about 10 minutes each. That should leave about 30 minutes for a discussion, which will begin moderated by me, but then open up to you very quickly. Okay, so Jesse, you can have the thumbs up. I will get out of the way.
Okay, well, hello everyone. From icy Cambridge here. Sorry I'm not able to join you in person. I'll have to make do as a disembodied voice. Going to step through this slideshow here on the potential limitations of renewable energy to help frame some discussion here. So as many of us have seen recently, we're seeing dramatic declines in the price of particularly solar and also wind energy, both on and offshore. in a variety of different markets. So just a roundup of recent headlines here from the United States, from Europe, from Australia, all highlighting the important declines in the price of renewable energy that just bringing these technologies into economic competition with conventional resources, including natural gas, even despite low natural gas prices here in the United States. Next slide. This chart from the U.S. Department of Energy shows the pace of cost reductions since just 2008, with significant cuts of roughly half or more in the price of both onshore wind and distributed and rooftop solar PV, as well as nearly 75% reduction in the cost of lithium-ion batteries, enabling more wide adoption of energy storage, which is seen as an important complement to variable renewable resources like wind and solar. Next. The recent report from UT Austin looked at the lowest cost generation resource on an LCOE, or levelized cost of energy basis, in each county in the United States, and found that for wide swaths of the country, actually, despite low cost natural gas, for new resources at least, wind and in many cases solar are the lowest cost resource now in large parts of the country, which is an important step of progress. I remember back in my days working as a renewable energy advocate in Oregon, no such thing was the case, and we were thinking very carefully about the kinds of public policy measures that are necessary to spur the adoption of these resources. And largely due to those policy supports, we've seen growth in renewables and declines in cost, which are helping enable more widespread economic competition. Next. So now we're hearing increasing calls, given the progress made in renewables, to push all the way towards 100% renewable energy. This is coming from both some academic quarters as well as increasingly various advocacy organizations, and even legislation being introduced in places like California and Massachusetts to require 100% renewable electricity from utilities in those states. So are we poised now, with wind and solar becoming ever cheaper, to drive all the way to 100% renewables? I would argue in this presentation it's not quite so simple. Saying that wind and solar are cheaper than natural gas or nuclear power plants is a little bit like saying an apple is cheaper than a slice of pizza. That might be true, and it provides you some valuable information, but it's hardly enough to make your dietary purchasing decisions when you go to the grocery store or plan your complete nutritional diet. Next slide. Levelized cost of energy is often used to compare between different technologies. We see this time and time again. This is data from the US EIA, but you'll see similar graphs from Bloomberg, from Lazard, from the IEA, from many others. And these imply, of course, that you can compare straight across these technologies. When in reality, levelized cost of energy is a measure of the cost of a technology or a resource. Its appropriate comparison is only to the value in the particular system of that same resource, not to other technologies that may have very different values. So back to our apple and pizza analogy, you may value a slice of pizza quite a lot more than an apple and be willing to pay more for it. So the fact that the apple is cheaper is only half of the information you need. What you also need to understand, next slide, is a comparison between the marginal system value of this resource and its marginal levelized cost as you deploy more and more of it. Here I'm borrowing a framework from Leon Hirth in Germany, but it's a simple concept that is, from basic economics, that we essentially want to find resources whose marginal value exceeds their marginal cost and deploy them to the point where those two are equal and no further. Marginal levelized cost, as we deploy more and more of a resource, may be going up or it may be going down as we either use up more high quality sites and move to lower quality sites, and therefore the cost goes up, or as technological progress drives the cost down. So the slope of that levelized cost line may change over time. But as we increase the penetration of a given resource in the power system, its marginal value falls as well. And this is nothing unique to electricity. This is true for anything. The first Snickers bar you eat is certainly quite delicious and adds a lot of value. The 10th or 11th might make you sick. So we have to think carefully about the marginal value of these resources as we increase their penetration. Next. Furthermore, the energy system or the electricity system is a system, and it involves multiple components, each playing different roles in the power system. Historically, we've categorized resources in different classes according to their total utilization throughout the year, their capacity factor. And that's been broken down into things like baseload plants like coal or nuclear, so-called intermediate peaking plants or intermediate plants like natural gas combined cycle or some older, less efficient coal plants, and then fast peaking units like gas, hydro, or combustion turbine units. Now, next slide. The trade-off here is basically between higher capital costs and lower variable cost, which argue for using a resource at a higher utilization rate, or lower fixed cost and higher variable costs, which argue for using it at a lower utilization rate. It's sort of like the trade-off between buying an efficient, fuel-efficient vehicle that might cost more upfront but save you on gas versus a less fuel-efficient car with a lower purchase price. So this has been the typical economic example of a so-called screening curves that compare the least cost resource at different utilization rates. And for low utilization, we'll want a peaker. For medium utilization, we'll want intermediate plants. For high utilization, we want baseload plants. And that's why we end up with a mix of resources in our current system, even though one resource, like say coal or now natural gas, might be the cheapest overall. That still doesn't mean that natural gas combined cycle plants dominate the entire resource mix. We have to think about their value in the system and how they're utilized. Next slide. Going forward, however, I would argue that these typical categorizations are no longer appropriate given the growth of variable renewable resources like wind and solar, which are becoming an even more important part of the energy mix. So here I propose three different classifications for resources to update the typical baseload intermediate peaker concept. The first is a flexible base of resources. That could be nuclear power operating flexibly as it does in Germany, France, Belgium, and Canada and elsewhere. It could be fossil units with CCS. It could be biomass if capable of operating at high capacity factors, or hydro systems with long seasonal reservoir storage that can operate as a baseload type resource, but flex their output to integrate variable renewables. On top of that, we have what I call our fuel savers, essentially variable renewables at high penetration level, which have relatively low capacity value, but reduce the need for variable costs and fuel from other resources when they're available and able to produce power at zero variable cost. So that includes wind, solar PV, and run-of-river hydro, as well as solar thermal with only a few hours of energy storage. And then finally, we have what I'm calling fast flexers. I removed the term peaker because they're no longer simply meeting peak demand, but meeting the peak in net load, the amount of demand minus the available renewables, and operating much more frequently to provide flexibility needed in the power system. So this, in a zero carbon world, are things like storage, demand response, or maybe biogas peakers, and in our conventional system, open cycle gas turbines. Next slide. Each of these resources now works together in concert in a low carbon power system mix. Here's an example of a week's worth of economic dispatch and unit commitment decisions from a model we've run on my team here at MIT with 1 gram per kilowatt hour emissions limit. So, 99.5% reduction in CO2 emissions, almost zero carbon. And what we see is a flexible base here provided by flexible nuclear, which does operate at a high capacity factor, but does ramp down on a relatively frequent basis, not daily, but almost so, in order to absorb inputs or outputs from solar or wind. Then in the middle, we have a significant role from fuel-saving variable renewables that move up and down as the availability of the wind or solar resource changes. Finally, above that in red, we have a variety of different fast ramping resources, including storage, virtual energy storage or flexible demand that can be scheduled throughout the day at different times, as well as demand curtailment or DSM, which charges and discharges to integrate the rest of the energy system. Each of these resources, as you can see, fills an important niche in the power system. We have a variety of technologies in each niche that can compete with one another, but act as weak substitutes for the other category of resources. Next slide. If we try to make any one of these resources play a role they're not well suited to, it's a little bit like fielding an NCAA basketball team with all power forwards or all point guards. Sure, they can play basketball, but they're going to lose to a team with the right balanced mix of players in the roles in which they each excel. Next slide. So as an example of this, here's the same week of demand with a mix, and again, the same emissions limit without any flexible base resource. First of all, note that we've scaled the y-axis here by 2.5 times, indicating the significant overgeneration here from variable renewables, and also periods of significant undergeneration when we have to rely heavily on those fast rampers for roles that they're not really well suited for. So we have long periods when energy storage is absorbing huge excess amounts of renewable output, long periods, full days even, when they're producing, when they're discharging, as well as a significant reliance here, the top red bar, on demand curtailment or price responsive demand in order to get through these periods of very low renewable output. So this is possible. We can do this, technically speaking, but it's a much more difficult mix to work, and therefore increases the costs and technical challenges of reaching deep decarbonization goals versus a more diverse mix. Next slide. Recently, along with Sam Thurmstrom, I reviewed 30 different articles and studies from recent literature on deep decarbonization of the power sector, spanning a whole range of different contexts, all published since 2014, when the last IPCC review was released. And we summarized those findings in this report, which you can find online, we released last week. Next slide. The core finding, which agrees with my own power system modeling research, is that there's strong agreement across the range of recent literature that a diversified mix of low CO2 generation resources offers us the best chance of affordably achieving deep decarbonization. Next slide. And that, furthermore, the research, is particularly those looking at very high penetrations of renewables, identifies 5 key challenges or limitations facing deep decarbonization when we rely overly on very high shares of variable renewables. Next. The first challenge is the marginal system value of variable renewables falls steadily as their system penetration increases. This is essentially because as we include in it the first increments of these fuel-saving variable renewables, we help displace the most high variable cost resources that are generating at that time, perhaps a natural gas power plant or a coal plant. This delivers significant value in the savings of fuel and CO2 emissions in a low carbon context. But as we deploy more and more of these resources, their power generation concentrates in the periods of high wind or solar availability. And in those periods, we eventually displace all of the high variable cost resources and end up competing only with other low variable cost resources like nuclear, hydro, or other renewable output. And at that point, the marginal value of these resources falls tremendously. So from a range of studies, for solar PV, we see the value drops by roughly half at just 15% of the annual energy share, and by nearly 70% if solar supplies 30% of the energy share, or roughly on par with natural gas or coal in the US mix today. Next slide. This is true even with energy storage, which is widely seen as a panacea for the intermittency problems of renewables. That's not the case at high penetration levels. So these 2 studies from Leon Hirth and from Andrew Mills and Ryan Weiser at LBNL show the impact of large amounts of cheap energy storage on the decline in the marginal value of these variable renewables. And as you can see, there's some impact, but it doesn't reverse the trend. So having storage helps, but it's not a panacea for this challenge, and we can show you more about why in some of the further slides. Next. At the same time, when you get to very high shares of variable renewables, what we end up being challenged with is both periods of very low renewable output level when we need to rely on storage or demand response to get through these lulls, or as well as on periods of excess power production. As we try to drive more renewables into the system to increase our output during the periods when wind and solar is low, we also dramatically increase the output during periods when wind and solar availability is very high. This leads to significant curtailment or wasting of available renewable resource levels at these high penetration levels. And this is a nonlinear effect that rises exponentially as we drive towards zero emissions with 100% renewables. So this is results from Bethany Frew et al., one of Mark Jacobson's students who's now at NREL, that shows the amount of curtailment across the United States in a high renewable scenario. And as you can see, as we go to 80 or 100% renewables, we're now wasting enough energy to supply somewhere between 1/10 and 1/2 of all of the energy generated in 2015. So we're essentially over-generating by half as much as we need and wasting all of that output because we simply can't absorb it. This is even with significant amounts of energy storage and flexible demand in the form of EV charging, which can be scheduled to match the output of wind and solar. Next slide. If we interconnect the entire United States energy, all the energy regions or electricity generation regions in the US, we can reduce this curtailment somewhat by aggregating output and shifting power from areas where it's not needed to areas where it is needed. Next slide. High renewable energy scenarios, of course, also entail significant expansion of long-distance transmission grids. This is for two reasons. One, to reach into the high renewable resource quality zones, which tend to be far away from demand centers in deserts or high wind locations, and also to help interconnect different regions and spread the variability of demand in renewables across the country. So for example, to reach an 80 or 90% renewable electricity scenario, NREL's Renewable Energy Futures Study proposes a 56 to 105% increase in US long-distance transmission capacity. In other words, roughly doubling the existing high-voltage grid throughout the United States. Next slide. In an excellent study on how to integrate these resources across the country, McDonald, Clack, and others in Nature Climate Change also envision a continent-spanning high-voltage DC supergrid, which would link all of the regions in the country along the same lines as the NREL study. Next. And Bethany Frew et al. Also envision a similar high-voltage grid, which would link power all across the country and be able to shift power for thousands of miles, particularly from high wind resource areas in the Midwest into the eastern United States. If we think about the total cost of transmission expansion in terms of the total system cost, these costs are relatively modest. The power grid, the transmission system today might make up 5 or 10% of the total cost of delivered energy, so even doubling that may only be a 5 or 10% increase in total cost. So the challenge here is not really one of cost, it's one of feasibility for siting and expansion and the land use impacts associated with roughly doubling the size of the US electricity grid in order to achieve these high renewable energy scenarios. Next slide. At the same time as they need significant expansion of transmission, these high renewable scenarios still depend on a significant capacity of flexible base and fast flex resources which can supply on-demand power. Here's the energy mix from the renewables future scenario, which sees a huge share of demand supplied still by these flexible base resources and a large increase in energy storage. And the result of all this is a significant overcapacity of resources. We see the total installed capacity in the United States in this system increase by 70%, despite the fact that energy demand is roughly flat in these scenarios. And the result of overcapacity is very low utilization rates for all resources, which means higher levelized costs for each technology in the energy mix. And that means higher overall system costs. Next slide. Or if you want to get rid of the flexible base resources, some studies like Jacobson's work or one of his students, Mark Becker, also look at how to do this only with energy storage without flexible base resources. And what they find is that we need several months worth of energy storage. So it's not enough to just shift energy around within the day to move solar power from daytime to nighttime, for example, or wind power from the middle of the night to the day. We need weeks worth of energy storage to be able to ride through seasonal variation in wind and solar output, or weeks-long lulls in wind output due to high pressure fronts that sit across wide areas of the United States and persist for some time. For comparison, next slide, all the 10 largest pumped hydro storage facilities in the United States, which make up the majority of our energy storage capacity installed to date, can supply US average energy needs for only 43 minutes today. So we're talking about going from minutes worth of energy storage today, maybe as much as an hour in total, to several weeks or months worth of energy storage. And just to give you a sense of that scale, this is a picture of the pumped hydro storage capability at the Grand Coulee Dam in Washington State. Next slide. What that dam does is pump water from behind the giant Grand Coulee Reservoir system, which is in the upper right part of the figure, up into Banks Lake Reservoir, which is a 27-mile long lake, which supplies 27 gigawatt hours of storage, or just 3 minutes and 30 seconds of storage for average US electricity consumption. And just to give you a sense of this scale, let's zoom out on the next slide. Here you can still see at this scale the length of the reservoir that provides just a few minutes of US energy storage. And one more slide. You can even see it from space. So when we try to get our heads around the scale of energy storage envisioned in some of these scenarios, I think it's worth keeping in mind the scale of pumped hydro, which is our largest long duration energy storage option we have today, and the kind of impact that would have to deploy months worth of energy storage on the power system. Next slide. So not surprisingly, the cost of renewables-only pathways to deep decarbonization rises steeply and non-linearly as the challenges described previously mount as we drive towards zero carbon. So, the challenge is relatively modest if we're trying to reach only 40 or 60% renewable energy share. But as we move from 80 to 100, the challenges I talked about before really kick in. And we start to get significantly rising costs. These are the low and high end estimates from the scenarios from Frew et al. Study for the United States. And as you can see, we're talking about dramatic increases in the annualized cost on the order of 5 or 6-fold over lower renewable energy penetration scenarios. Next slide. So it's perhaps not surprising then that of the 30 papers we surveyed in our lit review, the only scenarios for deep decarbonization that don't include a significant contribution from these flexible-based resources are the ones that decide a priori or at the outset to exclude these resources from consideration. In other words, the only way you end up with a 100% renewable type scenario or even 80 or 90% is if you demand that that's the only route to go. Any of the scenarios that include least cost optimization from an available set of resources, including flexible base, always include a significant share of these resources because it makes the challenge of deep decarbonization significantly easier and doesn't require pushing renewables out of their comfort zone or out of their ideal mix in the energy system. Next slide. So why make the challenge any harder than we have to be? We have a range of different resources, each providing different roles in the energy system. Wind and solar will play a significant role in the future power mix and a growing role relative to today, but primarily as fuel-saving resources working in concert with and in symbiosis with both flexible-based resources and fast-flexing reliability-type resources. And a balanced mix is clearly the best way to increase our chance of achieving deep decarbonization and to reduce the costs and technical challenges of getting there. Next slide. Just to leave you with one final note, I also want to point out that the path to zero carbon emissions may not be a straight line. What I'm showing here in this graph is results from one of my papers with colleagues at our National Lab looking at the value of energy storage in reaching deep decarbonization goals. The solid lines are the total share of wind and solar in the energy mix as we tighten emissions caps down towards 90% reductions in CO2. And the dotted lines are the share from nuclear playing a flexible base role in this study. And as you can see, there's some both nonlinearities and non-monotonic growth, meaning we grow initial shares of renewables increase, but then decrease as we go towards zero emissions. Other studies see the same effect for the role of natural gas as a bridge fuel, or even the role of carbon capture and storage if the capture rate is not close to 100%. So if we're only capturing 60 or 80% of the CO2 emissions from a power plant. So the optimal role of these resources may be different to meet modest emissions reduction or immediate emissions reduction goals as they are to meet deep decarbonization goals, which are our end target. What this argues to me is that we need to keep our eyes on the final prize, which is zero emissions in the power sector as soon as possible. And we need to plan pathways that get us there without risking overbuilding certain assets that will lock us into a suboptimal mix for getting to the end goals. So I'll leave you with that, and hopefully we can have a further discussion via the audio if we can get it working on this end. Thanks for including me, and I'm disappointed I wasn't able to be there in person, but happy we can converse virtually. Thank you.
Well, that was a wonderful presentation from Jesse, and I'm really sorry that he couldn't be here with us today. He's done really great work in this field over the last few years, and really is a presence. I work with a group called Energy Innovation, which is kind of unusual beast. We're not like a classic NGO working directly with policymakers on very specific policies and things that need to be done today. And we're not academics looking at kind of having the time to do a lot of deep modeling, like the nice work that Jesse showed you for his modeling of a Texas-like grid. But we do get to do a fair amount of our own research and our own analysis. My background is as a physicist. I worked on quantum gravity for a long time before I decided to work on climate change, and specifically the decarbonization of the electricity sector, starting a little over 10 years ago. And I spent some time at the DOE. as a AAAS fellow, and I even worked on that NREL, Renewable Energy Futures study as a outside referee. I think Jay Apt was also on that group of people. And things have really changed since 2009. So I'm here today as a kind of dissonant voice. So I know it sounds kind of funny because it seems like renewables are always winning out there. But in the group of people who think about long-term 80, 100% penetration type, full decarbonization, there's really, it seems to me, a kind of consensus that you can't get there with renewables. And I think Jesse did a very good job of presenting that viewpoint. And so I don't share that view. And yet I don't have a lot of detailed modeling to conflict with what Jesse has showed you. So how can I be up here talking to you this way? Being a theoretical physicist, having worked at Caltech, I'm a big fan of Richard Feynman's, and he talks about how it's very important not to get fooled, and the easiest person to fool is yourself. And so for somebody like me, the kind of work that Jesse and others are doing is very important because it gives you a target, something to think about. Okay, well, what are the exceptions, and so on. But the other things that a physicist does is try to think about the big picture, kind of some of the broad concepts that kind of inform what you're doing and not get too stuck in a modeling framework or a particular way of doing things. And I think that's very important. I often find that there's a lot to critique in any one piece of work, even the high quality stuff that Jesse showed us. And sometimes the critique aren't just on the edges. They're pretty important in terms of what the implications are. And so let me present my positive case for why I think renewables are really a very promising technology for having a big share, maybe a bigger share of that mix than Jesse talked about, maybe even a full share of the mix of resources that give us a zero carbon grid. So the first reason to be excited about renewables is they scale fast, okay? So just to give you an idea, when you think about a disruptive technology, you usually think in terms of S-curves. S-curves is like a 1 over exponential, one over a constant plus exponential type thing. It starts like an exponential, it levels off, and then it, in terms of acceleration, and then it levels off at some maximum penetration. So here on this graph, I've got some historical data for the last 5 years of solar deployment. And then I try to ask myself, okay, how would I fit this to an S-curve given the data I have? So for an S-curve, you have basically the exponential that you started with at the beginning. Well, that we can roughly say, for example, this is solar PV, the deployment rate has been floating around 40% a year compound annual growth. You have to say where you're going to end up, and you have to say what year you're going to kind of level off. Where does this S-curve go flat, and then the acceleration goes the other way? Okay? And now one of the early critiques of renewables from Jesse and Armin Cohen, for example, was that you just weren't going to be able to deploy them fast enough to attack the problem. These big, huge CCS and nuclear things, you can plop them down, plop, 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 and we'll take care of the problem. These wind farms and things, they're small. Well, look at these deployment curves. So this would be, so I have a final state of 10,000, 5,000, or 2,000 gigawatts. 10,000 gigawatts of solar at current capacity factors would roughly cover all of generation today. So not future generation, especially with electrification of vehicles and things like that, but just to give you a sense of scale, 5,000, half of that, and 2,000, obviously 20%. And I just want to show, so I think last year, I've seen different estimates, but the one that stuck with was 96 gigawatts of solar installed, though I've seen a slightly smaller one recently. It's close enough, okay? So that's the current deployment rate. Okay, in an earlier paper of Armin's normalized for global GDP, whatever. There's different ways of normalizing this stuff. This is already pretty fast. Okay, and you can see that in that like renewables are now almost like half or more of new capacity that gets installed. And the question is, well, how much faster do we need to be able to deploy this stuff? right? Well, if I'm going for the go crazy scenario, that red line, I'm gonna plateau. My maximum deployment rate is going to be in 2026, and it's going to be 8 times what we have today. Is 8 times what we have today technically a real big problem in terms of deployment? Well, it's just a bunch more factories in China and elsewhere. In terms of the kind of making the stuff, getting it out there, not a huge problem. Obviously, that's just the beginning of things. At this kind of deployment rate, you have to replace other stuff. I mean, replacing things is a lot harder than replacing new capacity. But at half of what we need today, it's the maximum rate's 4x, and at kind of less ambitious levels is 20x. What's interesting is, to me, when I was doing this analysis, is how quickly this turnaround is. So basically, within 5 or 10 years, we'll have a sense of which of these S-curves we're on. I mean, it's hard because real data doesn't look like smooth curves, and so extrapolation is a little harder than people might make you think. But it's going to take place soon. And the takeaway from this is these are very scalable technologies. We can get them out there fast. And we know from the lectures that we had this morning, the excellent briefings, that we need to get moving. We need to get this done. We don't have a lot of time. And so one thing that's nice about renewables is you can get them out there fast. The other nice thing is the cost drop. So in 2009, I was working on the Renewable Energy Futures study. It was a pretty interesting study, and it showed that we could get to 60–80% renewables for the US at not that much extra cost. Okay? But look at where the cost of solar was back then and where it is today. Okay? Average around 55. I know this is LCOEs, and Jesse's given you some of the caveats for that, but still, we've gone from $355 a megawatt hour to $55 a megawatt hour in this time. Okay, we were not expecting these kinds of drops, and we were still kind of committed to this course. Now, what does it mean to have cost drops like this? Well, we were expecting to be at 55 like 10 years from now, not now. Okay, and 55 is what almost 1/6 or 1/7 the cost. Now, you saw a graph from Jesse where, the kind of apocalyptic scenario of 100% renewables was 40% curtailment. Now think about it. Suppose it was 50% curtailment. Okay? That means I lose half of what I have. Well, if my cost of creating that resource is drop by more than half, what do I care? Okay? Utilization is a problem that's all over our economy. Okay, it's not just like directly in the power sector. You have to think about utilization of gas storage, of gas pipelines. You saw the Grand Coulee, footprint, but think about the footprint of our methane extraction. I mean, when I flew from California to here, I see just miles and miles and miles of pads and whatever all over. It's very visible from the airplane. Okay, so when you think about the energy system, you have to think about the whole. You really have to think about the whole envelope of it. If you're thinking about nuclear, you have to think about where the fuel's coming from, where the stuff is being stored afterwards, the waste, and also some of the risks. Recently I saw that for Fukushima, it's going to be $188 billion of cleanup, just for the cleanup. So this cost advantage is very important. Let me give you another example. So in California, we're dealing with something called the duck curve. Everybody's kind of running around like headless chickens talking about this because this year it's really taken off. Okay, we're really starting to see some ramps. We saw a 12,000 megawatt ramp last December. Okay, and you're hearing like Steve Burbridge, the head of the California ISO, say crazy stuff like, "Oh, the bills could be 6 times higher." Now you've got to keep this in perspective. Okay. Let's say for a 12,000. Suppose I just dealt with this 12 gigawatt ramp with just pure storage with 3 hours. Okay, so say 36 gigawatt hours of storage. Except I can go from -6 to +6 gigawatts, so I need half of that. So 18 gigawatt hours of storage. And we heard Elon Musk of Tesla fame just tell the Australians he could put $250 a kilowatt hour storage to solve their problems in South Australia. Okay, so suppose he came to California where he actually lives and dealt with this. You're talking about $4.5 billion worth of storage. Well, that seems like a lot of money, but we consume 250 terawatt hours of electricity in California. So if you amortize that over all those things, it's something like $2 a megawatt hour. Yeah, and $2 a megawatt hour is pretty cheap. You know, when I get power to my house from the big power grid, I pay $70 a megawatt hour just to do the transmission and distribution. Okay, and so, you know, when I'm dropping my price from from 1 year to the next by $5 or $10, that gives me a lot of room. Okay, so think about this graph as room to maneuver, room to get things done with. Okay, a couple more concepts. One is, we've heard about seasonal problems with renewables. We've heard about daily problems with renewables. We've heard about several week lack of energy from renewables. Well, those are real problems, okay? But one problem we don't have is year over year production of renewables. Renewables are very, very steady resource when you think in the power spectrum on an annual basis. So here I've taken the generation in the WEC of things that are just dispatched. So nuclear, hydro, and renewables tend to be just dispatched as they are available for the most part. And you see, nuclear is a very steady, reliable resource. Hydro is all over the map. Hydro is a problem for the West. Okay, some years you get tons of it, some years you don't, and mostly we're dealing with that with gas. Okay, so for hydro, this annual production issue is an issue. But for renewables, it's a very, very steady climbing exponential. You see one little dip here. We had a wind drought in 2015 where there was just a fair bit less production. But these aren't like massive dips in production. And if you go back in history of the nuclear fleet, you see here, I don't know, about a third of the way from the beginning, a little dip there. So this is not crazy amounts. So the problem that we need to solve with managing variable energy from renewables is bounded. Okay, it's just wanted to show you the hydro is not so bad on a U.S. scale. So the West has more variable hydro than you have here in the East. Also, it gives you a sense of just how quickly renewables are picking up. And let's go back. I just want to show you one more thing. So there was a lot of hand-wringing when San Onofre nuclear plant went down in California. And look, it's just a speed bump on the way up for renewable deployment. Okay, so that's on my slides. I wanted to make one last point, which is one thing a lot of these studies ignore when looking kind of into the future is the demand side. And I'm not just talking about demand side resources, which clearly do get integrated. I'm talking about long-term elasticity, okay? So for example, the California duck curve, it's a fall and spring problem. It's not a summer problem. In summer, we get more solar. It's a little later in the day. It's perfect, okay? Well, what do we do with all this extra energy in the fall and the spring? Well, we could start building industries around it, okay? We could start making fertilizers. We could start making electrofuels, power to gas, all kinds of things. Or just people could run businesses, seasonal businesses that use that energy when it's really cheap, okay? Why do we have Boeing in Seattle? Because they have really cheap hydro there, okay? So I think one of the things to keep in mind also, so to conclude, okay, really fast scaling technology, really fast dropping costs that buy you a lot of room to maneuver, and long-term elasticity can adjust to some of the problems that we've seen described in the studies. Okay, so those are the 3 points I want you guys to keep in mind. Okay, it's not a perfect technology. There are issues. We need to change the way we manage our power system, and I'm happy to address questions and talk about all these things. But I really wanted to I wanted you to keep in mind why a lot of people are putting energy and time and think that renewables with a high penetration are the way to go. And they're not people who are like in fairyland about the kind of problems that Jesse's talked about. But there's reason for optimism. All right, thank you.
Okay. I apologize for being the real disembodied voice in this gathering. I too am sorry that I was not able to join you in Pittsburgh. I was really looking forward to this gathering. And I was told we were not going to have webcam capability. I must have misunderstood, and I can't, so I'm on my wrong computer for that. I apologize. So I'll keep my comments as brief as I can, knowing how irritating it is to hear the disembodied voice coming into the room. I'd like to kind of just raise the discussion above the level of what's the path to kind of think about some global issues that I think are worth considering as we approach the topic of deep decarbonization. And I think Granger did a wonderful job this morning in his presentation, basically underlining the idea that this is an enormous lift, and we're not in a position really where we can safely discard any option from consideration. And fortunately, we're not at a point now where we actually need to discard any options from consideration. The constraints under which we are going to have to decarbonize globally, I think, are often misunderstood or glossed over. So the first of those constraints is economics. And I would argue that any strategy that entails rapid escalation in the cost of energy is bound to fail. And I believe that we have to find ways that allow us to decarbonize effectively at cost parity with where we are today. At the same time, we have to maintain the reliability of the systems that we're changing. So from the standpoint of the electricity system, which in the OECD and the West is very reliable, we can't move to a system that has degraded level of reliability. Looking globally, we have to be prepared to accommodate rapidly increasing energy use in the industrializing world. And the nature of that is going to be very likely to be a rapidly urbanizing world, a world that is going to be served by an integrated electricity grid, very much of the sort that we have here in the United States. The businesses that work to play in the energy transition are going to have to see a way to get their money back. And one of the points that should be taken from the presentation that Jesse made, and one of the things that's being discovered, is that when you slide down that marginal value curve, it becomes very, very difficult to devise a business model in which the investors in those technologies are able to get their money back. And if investors can't get their money back, the system will not be workable. The last bit that I think is really important to keep in mind is that public support for any kind of infrastructure build-out is going to be absolutely necessary. And I spent a fair part of my career as a project developer. I built natural gas-fired power plants, I built wind projects, I built electric transmission lines, I built natural gas pipelines. And the one thing that I learned is that none of it is easy. And everything that I worked on had some kind of opposition. And as every wind developer will tell you, it's very difficult to find a place where you will have smooth sailing in terms of permitting wind development. So another important point to take away from Jesse's presentation, the high renewable scenarios imply much larger systems than we have today to serve the same need. And I believe that those systems, one of the risks of such systems is that they will run afoul of public opposition. I wanted to just say one thing about sort of the, I think, humility that we need to have as we think about all of these studies, because we tend to kind of polarize ourselves into camps. We're the renewable camp or we're the nuclear camp. These are all guesses. These are all best estimates. These are all fraught with risk. And rather than settling on one path or another path, in my mind, it makes much more sense to say, all right, there are probably multiple ways that we could get to this endpoint. Let's have a frank and honest discussion about the challenges present on each of these paths, because each of them has significant challenges. And then just a corollary word about all of these studies. I've done a lot of studies that look a lot like the studies that Jesse has done, and I've been doing them for years and years and years. Even though most of us who do these studies have training as scientists or engineers. They're not actually science in the strict sense. They're informed by science, but really they're scenarios trying to help us better understand possible pathways to the future and the implications of different assumptions about those pathways. And so in that sense, they're very, very, they're bounded by a lot of uncertainty. And we often forget that, and we often act as if there's some kind of empirical solidity behind the work that actually really isn't there, and I think we need to be honest about that. One of the things that I just wanted to talk about the seasonal problems, and then I'll end it. I do believe that the production of seasonal surplus is a significant problem with high levels of renewables, and in spite of what our previous speaker just said, I actually do think that the bulk of the studies that have been done on this topic, including those that come from NREL, the National Renewable Energy Lab, all point to this as a significant concern, significant in the sense that we don't have good physical mechanisms for dealing with them today. And oftentimes, and the previous speaker said, well, we'll build industries around this seasonal surplus. And again, that could probably be done in an engineering standpoint, but that fails the business model test that I raised earlier. Alcoa moved its largest aluminum production facility to Iceland. And it did so because Iceland did a deal with them where they provide them with very inexpensive, around-the-clock, cheap hydropower. You can't build a capital-intensive industry and then only run it part of the time. That's just not the way these businesses work. You invest a lot of capital, and in order to get your money back, you have to operate that process more or less continuously. And you look from industry to industry to industry, and that's the pattern that we see. So you can't solve the problem of intermittence by building another even more intermittent industry on its back. That is just simply not likely to survive the business model test. So with that, I'll end my comments, and hopefully we can have a good discussion. Thank you.
My first experimental question is, will questioners from the audience need to use this mic or another mic, or should I relay? Two mics here. Okay, great. So what I suggest we do, thank you, Steve. And Steve and Jesse can both hear me, I believe. So on that assumption, what I think we should do, because we only have about 5 official minutes left, and we'll take 10 unofficial minutes. I'm still cognizant, though, that I have now become the last person standing between you and lunch. So we're going to keep it to 10. But I think what I would like to do is I'm going to relinquish most of my moderator prerogative and open it up to your questions. But while those questions percolate, and as the first questioner would like to kind of grab a mic, I'd like to ask a question back to Jesse. Jesse, can I get some feedback on whether or not you can hear me, or do I need to be texting this?
I think they can hear you.
They're just ignoring me?
We're not typing in their audio.
Ah, got it. Okay. Jesse, so I'd like to hear your response, because Eric laid it out and Steve picked up on it, and it also, I think, is relevant to one of your more interesting ideas that you laid out for the group, which is, in effect, this notion of renewables as a bridge, fuel to the future, and this nonlinear, non-monotonic possibility of the renewables curve over time. Could you please respond to this, the kind of the so what argument on utilization for renewables, and kind of expand on that a little bit? And if you want to kind of talk a little bit about the potential for stranded assets in that particular infrastructure in the energy system, that'd be a nice coda as well.
Okay, can you hear me again? I think so. So great question. I hear two things in what you're saying. One is given that we may end up with more renewables than we want for deep decarbonization if we plan only for the incremental goals of maybe 50 or 60% reductions in CO2, is there a risk for stranded assets? And I think that there are two risks we need to think about there. One is, yes, there is a risk for stranded assets. 2050 is not that far away in the cycle life of investments in power generation resources. It's basically one cycle from now, so that power plants built in the next 10 years could very well be operating in 2050. So I do think we need to plan carefully for a pathway from here to there and not just incremental targets along the way as if those are the end of the road. And so that means that, pushing towards 50% renewables as California and New York and other states are doing might be fine, especially if you have a good amount of hydro or biomass or geothermal that meet part of that 50% requirement. But starting to push beyond that may be a challenge and may result in higher shares of wind and solar than we might want, which means we may have to turn those units off in the future. The other risk, though, is that we don't invest significantly enough in scaling up the other flexible base resources, which won't appear overnight either. And so we need to be building industries around nuclear, around CCS with high capture rates, around engineered geothermal or biomass if we want to use those options, and building those up to scale as we deploy variable renewables and tap the opportunities we have there. So I think we need to think both about scaling the things we'll need in the deep decarbonization targets and not overbuilding variable renewables. In terms of the utilization rate question, I mean, Eric noted that, yeah, the price of renewables is falling, and if it gets cheap enough, then it's fine to waste some of that output. And that's true. And the reason we see a decline in the value of renewables is both due to the fact that they're not displacing as valuable enough fuel anymore, and at some point because the output is simply wasted and not utilized at all. But I think it's worth noting that, further 70 or 80% reductions in the price of solar PV is not an easy undertaking. There's a limit to how much we can get out of the cost of modules and system installation simply through business as usual scaling and learning by doing. And so if we really want to get solar or wind to these higher penetration levels, 30, 40% each, where they're as significant a player in the energy mix today as natural gas or coal, then we really need to be proactively pursuing not just incremental scaling, but next generation technologies and improvements, particularly in solar materials, that could give us very, very cheap solar that we could afford to waste half of the output from that. So, it's not a foregone conclusion that that's impossible, but even that still only gets these resources to a third of the energy mix or less. So again, it's a mix, it's a system. We want to have each technology playing the right role in the mix and try not to push them further than they should be, or we only increase the chance of coming up short.
Okay, thank you, Jesse. I think we have a queue, right? It's over here somewhere? Or no, right here. Thank you. And I'm supposed to announce that if you ask a question, you are being recorded, and so by asking, you're giving your consent to be broadcast on television, I believe you said. Yeah, so.
We're live streaming to the web, and we're recording for posterity.
Okay. Yes.
Okay. I'm Nina Dodge from DC Climate Action, as in District of Columbia, DC. My question has to do with urban systems of power distribution and generation. And given the context of 50% of population or over now living in the US, I won't talk about globally, in cities, and that projection increasing into the future. And I know we're looking at a relatively short future as we need to, but given that and the capabilities of what's the shorthand of which is smart grid, of two-way power flow, or of infrastructure that supports two-way power flow and communication grid infrastructure, and looking at really a more micro scale of delivery and generation and the potential of systems efficiencies that derive from the city model. I would, and of course we all know about the hype over Brooklyn, Queens, and a few other experiments, some in Southern California, in terms of locational planning, very, very granular locational planning. That has not been commented upon, And I really think it's important to comment on that, and I'd love to hear from various speakers on that aspect of the equation. Thank you.
So I think we need a technique for determining which panelist would like to. Jesse said? Oh, great, terrific.
Okay. So there are two main strains of my research, actually. This is a great question. One is deep decarbonization, and the other is the impact of distributed energy resources on power systems. So I was a participant, one of the researchers in MIT's Utility of the Future study, which we released in December. And you can find at the MIT Energy Initiative website, which dives in significant detail on the kind of question that you're asking about the opportunity for more locational siting of distributed resources, integration into distribution network management. In terms of this, today's venue and the discussions about deep decarbonization, I'll just say that I think these are, the trend toward lower carbon and the trends toward more decentralized resources, I think are separate trends. They're not overlapping, at least not to a significant extent. They overlap in the sense that distributed solar is both low carbon and distributed. And they support one another in the sense that having greater flexibility on the demand side is a key part of reaching deep decarbonization goals. But having a more distributed future doesn't mean we have a low carbon future. And in many cases, the most cost-effective resources from a system perspective to get us to deep decarbonization are large utility scale renewable resources. So large solar, not rooftop solar, which can be 2 or 3 times more expensive than utility scale solar. And large wind, which is one of the most cost-effective resources we have today, as well as, of course, large nuclear or CCS plants or biomass or geothermal or hydro. So we need to think carefully, I think, about both trends, about how to better utilize the capabilities of distributed resources to help reduce costs of energy systems. That might free up some money we can use to afford the cost of decarbonization. But driving towards a distributed grid won't necessarily get us to a low carbon system unless we also focus on that other objective as well very clearly.
Okay, David's hungry, so we're going to give Eric a chance to respond to this, and then one last question here. No cue, right? Okay.
Well, I would tend to agree with Jesse. And I think there is this kind of weird war between like this there's some people who are very attracted to the idea of a distributed system as a kind of liberation from the big bad corporate central system. And, I could see some of the attraction there. And I think distributed resources in terms of going to low carbonization, they can help you on footprint. You can generate some of the energy from rooftops and so on without having to use pristine or degraded lands. And they can help you a lot with flexibility, using EVs, distributed storage. Distributed storage doesn't have to have that $70 a megawatt hour tax of going in and out of the transmission system. I imagine an ideal system would have a kind of fractal nature to it where you were distributing storage all along the chain and managing the grid and kind of expanding cells. I think I want to leave you guys with the idea that I think a high penetration renewables grid is quite possible, but it will take pretty major changes in how we run our grid and how we organize regulating the grid. One last point about distributed, I'm a little worried about CHP. The problem with CHP is in the near term, it gives you a lot of emission savings because you're using a low, gas emits less than coal, for example, and then you're being more efficient with the waste heat. The problem is that you're distributed this thing that uses fossil fuel, and then there's no way to like hook on anything to it. At least a power plant, you could do the CCS, but you're going to go find all the microgrids, microgas all over the place. So that's kind of one worry about that approach.
Fuel cells?
Fuel cells. I won't go there.
Okay, thank you. Last question.
Dave Grossman. Okay, Dave Grossman, Green Lake Group Consulting. I wanted to pick up on one of the things Mark started with and ask about kind of the political realities. So, and this is going to be a theme that I'm going to hope to return to repeatedly throughout this whole conference. So we saw S-curves, we saw projections of various sorts for various technologies. how do political realities play into those projections? I would imagine those are one of the large factors of uncertainty that need to be factored in, particularly now, for some of these technologies that may require federal R&D dollars. We're hoping to still have national labs, but we don't know. A little flip, but only a little. So for these various projections about what's needed for deep decarbonization, how much of it can be renewables, how much we need the flexible base, et cetera, how realistic are those projections, and how do the political realities play into it?
Derek.
Look, the most important thing is we have no clue about what's going to happen beyond 5 years, and even within 5 years, like what did we know on November 2nd, right? So you have to kind of stick to some of the broader things and some of the lessons you get from the type of high quality modeling that Jesse's presented. One of the reasons I like renewables is the business case. Right now, there's 190 gigawatts of coal that costs more to operate on a marginal basis than subsidized wind. So subsidies won't be there forever, but the cost is still dropping. But that's a lot of coal we can move off now just by making the case, hey, if you shut down this coal and we could put wind, it's going to be cheaper. And for example, in Colorado, the coal's not really doing a lot of the load balancing work. It's the gas fleet, Xcel gas fleet, that's doing it. So it's really more, it's not an apples to pizzas issue so much. And so I think the political reality there is one of the states that's installing the most renewables is Texas. And in Texas, coal plants have negative cash flow. Gas plants can't cover their capital costs. But even at the crazy low wholesale prices that they have now, you can make a merchant, you could potentially do a merchant wind and come out ahead. And so I think that's the nice thing about renewables, and the cost structure is going to drive the system. Now, there's problems when you get to 80%, okay, 80 or 90%. And the question is, do the cost reductions, does the cost come down fast enough? Do the new technologies like storage or flow batteries and things like that come in and help you? Yeah, that's a good question. But in the near term, with the political environment we have, where nobody's paying attention to climate, renewables are great because they're cheap.
Great. No final word chime-ins from the two remotes? Okay, good. Well, thank you very much. I think it's now time. Thanks to our panelists, both here and kind of here. And turn it back over to him.
Thank you, Mark. It is lunch, which is right outside. Bring it back in, mingle for a little while, and then we have a great lunch presentation, a couple of presenters for the end of lunch for you. So thank you.